The discussion this session will be about probability once again, going into some slightly different topics than last time. Okay, what we're going to discuss are permutations, combinations, binomial probabilities, probability distributions, and expected values. Okay, we're going to look at kind of a self-referential problem here this week. So a survey, a fictional survey I might add, of incoming analytics students has shown that 89% of them have at least 5 years of work experience prior to applying. What is the probability that out of the 25 students in this particular class, 20 of them have 5 or more years of work experience? Okay, keep that one in the back of your head. Let's get into some details here. Okay, all of this week basically starts off with factorials. Okay, that's the basis of pretty much everything we're going to cover. And the good news about factorials is that they are relatively simple to explain, and you will never need to do the mathematics manually. So as gruesome as the factorials may get, you always have a computer or calculator that can help you with them. Okay, so all a factorial is, it's the product, as you can read on the screen, of whole numbers in decreasing order. Okay, so a factorial is given as an exclamation point, and don't be confused, this does not mean 6. Okay, what it means is 6 factorial. So you multiply 6 times 5 times 4 times 3 times 2, and if you want to be complete, times 1. Okay, and for the record, that is 30 times 4 is 120 times 6, so 720 is 6 factorial, in case you were curious and wanted to do that one in your head. Combinations and permutations, often confused, but different enough that it's important to understand the difference. Okay, so combination is a particular arrangement of objects, not considering the order of the objects. Okay, whereas permutations, same idea as combinations, but order is important. Okay, and why am I telling you this? You'll soon see. So the difference between combinations and permutations is whether your stuff is in order. Okay, so mathematically speaking, and I will go, I promise, soon from the abstract to the concrete here. If we have n elements in our set and they are taken r at a time, then the permutations are n factorial divided by n minus r factorial. Okay, and the combinations, n factorial divided by n minus r factorial times r factorial. Okay, so they're one term for being identical. And that term itself is the number of things that you're choosing. Okay, so let's do a couple of examples. I know it's really difficult to understand in the abstract, which is why yours truly is an applied mathematician and not a theoretical mathematician. Okay, so let's look at how many classes full of 10 people can we possibly put together given 50 incoming analytics students. So we have 50 students coming in. How many different classes of 10 people can we put together? Okay, so the first thing you want to look at with any problem of this sort is, does order matter? Okay, and given that we're just putting together classes of 10 people, it really doesn't matter what order these people are in. Okay, so if order is not important, it's going to be a combination. Okay, so the combination here will be total number of people divided by the number of people minus the number you want in the set times the number in the set. Okay, clearly this is a lot of combinations. Okay, it's almost like when you're looking at, going back to last week, a deck of cards. When you have 52 cards in the deck, how many different 5-card hands can you make out of 52 cards in the deck? Okay, clearly there are a lot of different possibilities, more than you possibly think. Okay, altering the problem a little bit. Okay, now we have 50 and the same 50 incoming students, just for the sake of argument, wanted to enroll in classes. Okay, how many ways could these 50 students rank their choices of 400, 401, and 402 as first, second, or third? Okay, so there are 3 classes here, 50 students, and because we're talking about ranking the classes as first, second, or third, order is important. Okay, so in this case, the answer, as you can see, is 117,600. Okay. Also, clearly a high number, but not quite as high. And for argument's sake, if they were just ranking classes in any order, this would be a combination and not a permutation. And this would be a little lower. Okay, this would be about 20,000 possibilities if order were not important. Okay, so we're going to get back to that idea, but right now we're going to switch over to binomial probabilities. Okay, so if your chance of success in any single trial is lowercase p, then the chances of x number of successes in n number of trials will be the combination times the chance in the single trial to the xth power times the chances complement to the n minus xth power. Okay? It's a really nice, elegant equation, but it is limited to binomial experiments. Okay? And there are stipulations for what defines a binomial experiment. Okay? And they are: the same experiment is repeated a fixed number of times. Okay? So it's repeated n times. Okay? And as you noticed, by binomial, okay, that's bi means 2. Okay, it means that there are 2 possibilities of outcomes. Either you succeed or you do not succeed. Okay, that should say success or failure, not success of failure. Sorry about that. Okay, and the third stipulation is the trials must be independent of each other. Okay, and again, I cannot emphasize enough, this only works for binomial experiments, which you will see binomial experiments. They're not that uncommon, but you have to be very sure that you have a binomial experiment or this formula does not work. Okay, and just to make things a little bit worse for you, for some reason, statisticians cannot come up with any of the other 26 letters of the alphabet. So you have a lowercase p and an uppercase p. Okay, an uppercase p is the probability of success. A lowercase p is the probability of success in a single instance. Okay, and the order of the terms in the combination is opposite the order in the probability. Okay, so if you look back at that equation here, we have probability of x given n is the combination of n given x. Okay, so be careful, those get switched around. Okay, so enough of scaring you with all the bad stuff about this. Let's actually try one. Okay, a simple binomial probability is flipping a coin 10 times. Okay, and let's check over that it satisfies all of our stipulations. Okay, it's repeated a fixed number of times. Beautiful. We're saying we're flipping it 10 times. The possible results are indeed binary. You have 2 choices, heads or tails. Again, negating the fact that some people say they can get a coin to land on its edge. And the trials are independent. One flip does not affect the next flip, unless you're cheating. So what will the probability be of getting exactly 5 heads on 10 tosses? Okay, and it would seem like 5 heads and 10 tosses, it happens 1 out of every 2 times, so the probability should be 50%. It's not. Okay, the probability of exactly 5 heads really only occurs less than that. So the probability of getting 5 heads giving 10 tosses is the combination of 10, 5 times, okay, again, the probability of a certain outcome. Okay, the probability of either outcome is 50%. Okay, and we're saying it's going to happen, the probability of it happening 5 times, so it's 50% to the 5th power times the complement, which is 1 minus 50% to the n minus x power, which is the 10 minus 5th power. Okay, so this looks pretty symmetric because I only did it 10 times. So the probability of getting exactly 5 heads in 10 tosses is shockingly low. It's about a 1 in 4 chance of getting probability of getting exactly 5 heads. Okay, and that's kind of the simplest case example. Okay, things of course do get more complicated from there. Okay, what if I had asked you the probability of getting at least 5 heads instead of exactly 5 heads? Okay, to do this, and I'm not sure if this is intuitive or not, but to do this we need the probability of 5 heads plus the probability of 6 heads plus the probability of 7 heads plus 8 heads plus 9 heads plus all 10 heads. Okay, so what is this going to look like? Okay, the probability of at least 5 heads is the probability of 5 heads, as you can see it there, expressed mathematically. Okay, I'm going to leave the actual equations to you, which I really highly recommend you do on your own because it's just very instructive and it's a good learning experience to actually play with these equations. But the probability of 5, exactly 5, we said was 0.246. The probability of exactly 6, 0.205, and on down. So the probability of 10 heads out of 10 tosses, as you could see, it's a pretty small number. Okay, it's slightly less than 1 in 1,000. Not impossible, but small. Okay, so the probability of getting 5 or more heads, okay, it's around 3 times the probability of getting just 5 heads, which I think is pretty interesting. So think about what else you can kind of glean from this, and there's a lot of different things going on there. But we're going to go from probabilities, kind of a natural hop, skip, and a jump, to expected value. And again, sorry, I know these are a lot of gambling examples over last and this week, and that does not mean that I or Northwestern encourage gambling, but it's just a good way, an easy way to look at probabilities. And that's where expected value came from. Okay, it was how much you could expect to win basically at any different game of chance. So for those of you who have stepped foot in a casino, possibly you've thought about this, or you've disillusioned yourself into thinking that it was better than it really is. Okay, but let's look at a simple game in the sense that there's a set number of outcomes and it's a fair game and there's not a whole lot of different possibilities involved. Okay, and that game is roulette. Okay, for those of you not familiar with roulette, it's a spinning wheel with 38 different spaces on it. You drop a marble in and it lands on one of those 38 spaces. Okay, and the rub is that even though you have a 1 in 38 chance of winning, the actual amount the casino pays you is really as if you had a 1 in 36 chance of winning, which is why casinos have all of those big shiny buildings. Okay, so you're betting on roulette, and the odds of winning, as I mentioned, are 1 in 38 or 37 to 1, and the payout is 1 in 36 or 35 to 1. Okay, so keep those numbers in mind. Okay, so we're just betting on a single number in roulette. Okay, and generally speaking, the expected value formula, and we'll get back to the actual numbers in a moment, okay, is the possibility of the event occurring times the probability. Sorry, it's the probability of the event occurring times the amount of money that you win or lose if it happens. So it's the probability times the amount. And what you have to realize with gambling, or as with most expected value problems, some of the values will be negative and some of the values will be positive. Probabilities obviously always have to be positive because, as we learned last week, a probability must be a number between 0 and 1. So it has to be a positive number or 0. Can't be negative, but if you lose money on it, your net value is going to be negative. Okay, so this is expandable forever. You could have as many different events as you want. And if some of you have played other games of chance, you might have 7, 8, 10 different events happening, each of them with a different possible payoff. So you can have a lot of different events in the real world and a lot of different possible payoffs, but we're going to get back to our roulette example here, which is just 2 possibilities in our bet here. Okay, so we have a 1 in 38 chance of winning on our $1 bet. Since it pays off at 35 to 1, we will win $35. Okay, that's the good part. We'll win $35 if our lucky number happens to come up. Okay, unfortunately, there is a 37 out of 38 chance that our number will not come up. So it's a 1 in 38 chance it will come up, 37 and 38 against. We win 35 if it does come up. We lose $1 if it doesn't come up, which sounds great. You win $35, you're only risking $1. But when you do the math, what you see here is that for every dollar you bet, you can expect to lose about a nickel. Okay, so the expected value of a $1 bet on a roulette wheel is about -5 cents. Okay, and as I mentioned, it's really, really important to be aware of the signs. Okay, you have the negative sign there because the dollar is the amount you're going to lose, and the positive sign in front of the money you could possibly win. Okay, and the other important thing is you probably do not want to bet your life savings on a roulette spin. Okay, so let's get back to our slightly more complex example here. Okay, so we have a survey of incoming analytics students. 89% of them have at least 5 years of work experience. What is the probability that out of the 25 students, 20 have 5 or more years? Okay, so the probability that exactly 20 out of 25 will have 5 or more years. Okay, and what we're given an 89% chance, and this is, and you should check it, this is indeed a a binomial problem. It satisfies all of our conditions. Okay, either they do have 5 years or more experience, or they don't have 5 years more experience. We're looking at a fixed number of people. Okay, so everything is satisfied there. Okay, so if you set up the equation correctly, it's the combination of 25 and 20, 89% probability, and we're looking at the chances that 20 do, and the complement of 89% is 11%, and the complement of the exponent is 25 minus 20. So if you set that up correctly, these are the numbers you'll get. You'll get about an 8% chance that exactly 20 out of 25 analytics students have at least 5 years of experience. Okay, and again, that's made up numbers. I'm not basing this on anything that the admissions office has given me. Okay, and this might seem like a pretty low number, but remember, we're asking for exactly 20 out of 25. And now, for your own edification, you should check what would be the probability that at least 20 out of 25. Okay, so how would you set that up? Okay, you would need the probability of 1 out of 25 plus the probability of 2 out of 25 plus the probability of 3 out of 25, add it all the way up to the probability of 20 out of 25. So you'd have to do this 19 more times with different numbers. Okay, and the only number that would change here would be your exponent. Your combination number would change, and your exponent would stay. The 0.89 and the 0.11, they would stay the same, but your exponent and your combination would change slightly. Okay, so it would be interesting for you to just try out the possibility and see what you come up with here. And if you want, we'll discuss that in class.